Welcome, everyone, and thank you very much to Black Hat for having me. 50 years ago, in this document that you see here, we knew for the first time that corrupting the memory of a program could lead to taking control over the instructions that it executes. We didn't know yet, but this was the very first mention of what we know today as a buffer overflow. And since then, we, the security community, have gone so far, both defenders and attackers. On the one hand, defenders have created new, better ways of fortifying this memory. So we got ASLR, we got non-executable stacks. And on the other hand, attackers have always found new ways of bypassing these defenses. So we learn how to leak things. We learn how to do code reuse. But eventually, in 2005, academics introduced what we know as control flow integrity. This is a little bit different. And since then, these kind of defenses have slowly but surely gone into everyday systems. You could say they are already here. Control flow integrity takes a different approach from the classic defenses. Instead of trying to make exploitation more difficult, it actually tackles the problem at its root, which is the ability to control the instruction pointer in the program. So what they will do is to use static and dynamic methods to analyze your program, and it will construct what we know as a control flow graph. And this control flow graph will describe the transitions between functions inside the program. And after that, control flow integrity will instrument your program so that it actually forces these transitions to be the only ones that happen and not the ones that the attacker wants. And yes, this is a very significant level up from the defender side because, in essence, it prevents one of the techniques that we have been using for a very long time, which is return-oriented programming and every other code reuse technique out there. But of course, it is the time that attackers also level up again. So we're not the first to suggest a way of bypassing CFI, of course, but today we point out a new way of doing it in something that is in C++, coroutines. My name is Marcos, and I'm a PhD student from CISPA in Germany. I do research on system security and also malware. And yeah, I have a couple projects around, so just check them out if you are interested. This project has been developed thanks to my supervisor, Christian Rosso. He's the leader of the system security group. And together in CISPA, we do very awesome things. So feel free to reach out. We have very cool projects, and we're very happy to have feedback about it. This is what we're going to do today. First, we're going to go very quickly, because this is not a CFI talk. We're going to go over the existing user space CFI defenses. So we're going to go over how they work. After that, we'll look into how these coroutines actually work under the hood. And we'll underline certain things that I consider to be very interesting. Then we'll actually have fun, because we're going to take these primitives that are for insecurity primitives, and we're going to do attacks with them. And finally, we'll suggest some defenses. So let's go. The first and probably the most popular one out there, the most popular CFI scheme is Intel CET. It's hardware-assisted, and it's coarse-grained, meaning that the instrumentation that is in the program is not so strict in terms of enforcing the control flow graph of the program. But it's basically two-in-one. On one hand, we have substack. And this basically happens every time you're calling functions inside the program. So you will have something like when you're calling one function to another, you will push the return address to the stack. And this happens for every function. And in a separate memory page, which is not accessible by the rest of the user space, you will have what we know as the shadow stack. And this is not accessible by the normal user space, but will only store the return addresses. And when you're returning from the functions, you will compare the values. If they are the same, all good. If they're not the same, then you will have a fault. And this might happen because you might try to override the return address, right? The other complementary part of Intel CET is indirect branch tracking. And this one is for protecting indirect pointers and indirect functions inside the program. So essentially, we can, of course, override the indirect pointer in this case, and you can jump wherever you want. But with indirect branch tracking, what you will have is a landing path based on an NDR instruction that is compiled with your program, and it will enforce that every indirect jump always lands in one of these instructions. So you can essentially only call functions from the very beginning. Then we have control flow guard. And it turns out that IVT, although Windows does have CET, IVT is not in Windows. They decided to go this other path, which is essentially equivalent. But it's not hardware supported. Instead, it's software. It happens during the compilation of your program. So it will translate every single indirect call in your program to a direct call to this other function that you see here. And in this function, there will be a series of mathematical operations that basically check against a 2-bit map that tells you whether this call is allowed or not. And the most important one is if you have 1, 0, and this will tell you, OK, so you can jump to this function from the very beginning. So if you check out probably any function in any DLL, you will see, oh, it has 1, 0, meaning that I can call it from the beginning. Finally, we have not only coarse-grained CFI, but also we have more fine-grained stuff, like LLVM CFI. And in this case, what it will do is to compute the some kind of dynamic type of every indirect pointer. So let's say you have this indirect function that is assigned to this other function, like close. And what it will do is to define a prototype based on the return type of the function and also the arguments that it has. And it will enforce that every call goes to functions that have the same prototype. OK, so let's actually look into what is a coroutine. Coroutine is a function that can suspend and resume. What do I mean with this? When you have a function, you execute the function, you go to the function, execute it completely, return, and that's it. And if you execute it again, you will actually go to the function from the very beginning again until the end. But with a coroutine, we have what we know as suspension points. And suspension points are points in which you say, OK, I want to hold here. I will maybe resume it later. And if you actually call the coroutine again, you will not go from the very beginning, but rather you will go to the suspension point where you left it, and from that point you continue. So there are certain things that you have to do when in C++ to implement coroutines. One of them is the task object, and you can imagine this as like the topmost object where everything in the coroutine is contained. Everything else that I'm going to explain to you now is contained in this object. For instance, we have what we know as a coroutine handle. And the handle is a pointer to the coroutine. So basically, it will allow you to access the coroutine and do things like resume it, meaning that I want to go to the last suspension point and resume it where I left it, or destroy it, meaning that I'm done with these coroutines and I will leave it and I will never be able to resume it again. For a function to be a coroutine, it needs to have one of these 3 different operators. If you have them, then the compiler will identify it as a coroutine and generate different functions that I'm going to explain to you later. The first one is call yield, and this is the most basic one. Basically, you reach it, and you return a value. And this is also counts as a suspension point. And then you have call return, which is basically the return equivalent in a function, which basically allows you to return a value to, and you're done with the coroutine, and you will never be able to resume it again. Now, returning values works funnily in coroutines. So actually, there's something we call the promise. And this promise is some kind of objects where the coroutines and functions have a shared space for sharing data. So every time you return a value, for instance, you save it in the promise, and then the function later takes the value from the promise. So when a coroutine is compiled as a coroutine, 3 different functions are generated in the background, which I call the stubs. The first one is the creation stub. And it creates an object that I will explain to you later that defines the whole context of the coroutine. The second is the resume stub, which is in charge of actually resuming the coroutine. And the third one is the destroy stub, which is the one in charge of destroying the coroutine. We'll go deeper into this later. So just to have an intuition how this looks in a real program, you have the task objects, the handle inside, the promise that I told you about, and inside this promise you have the return value, and some other functions that allow you to do some customization, like, OK, what happens when the coroutine is initially suspended and what it is finally suspended. Typical stuff that programmers use with coroutines. Now, coroutines in C++, and this doesn't happen in every programming language, are stackless. This has certain implications for programmers, but for us, what this means is that the coroutine is only able to suspend inside the coroutine and not in another function. So imagine it calls another function, you cannot resume from this other, you cannot suspend from this other function. And really, the main implication of this is that the compiler can generate a very optimal way of storing everything related to the coroutine in memory. Specifically, every time you have an instance of a coroutine being executed in your program, you will have what we know as a coroutine frame. And this is a heap-allocated object, and you will have one for every coroutine that you're executing in your program. And it looks like this. So you have the handle, and the handle points to the resume pointer. Sorry, it points to the coroutine frame. And in this coroutine frame, you have different things. The first one is the resume pointer. And this pointer will point to the resume stub that I told you before. And it's actually an indirect call, meaning that every time you resume the coroutine, you will have an indirect pointer. The second one is the destroy pointer, and it points to the destroy stub, similar like the resume stub. And it also is an indirect call. Then we have the promise, where you save the return values, etc., and the parameters. And this means that every time you're calling a coroutine, like if you pass in some value or some pointer or whatever, it will actually be stored in the coroutine frame. And then we have the variables. And this requires you to change your mentality, because usually when we are executing functions, you know that everything is in the stack, right? So everything is going to be addressed by RSP, RVP, and you're going to have all the variables there. But in a coroutine, everything is directly in the heap. Like everything's in the heap already. So every stack-based variable, it's actually heap-based variable. And every heap-based variable is a pointer in the coroutine frame that points to another coroutine, to another heap-based object. Final element in the frame is the coroutine index. And this is an integer number that tells you whether you have, on which suspension point you have to resume the coroutine. So, for instance, 0 will tell you, OK, from the very beginning, or another number will tell you, OK, from another suspension point. So what's really this stubs? The creation stub is a call to malloc, because you need to allocate the coroutine frame, right? So every time you actually create a coroutine and use it for the first time, you're going to have a call to malloc. And in this malloc, after this malloc talk, you will initialize the coroutine frame with the resume and destroy pointers. After that, you have the resume stub, and it's like a switch. It will take the coroutine index and say, OK, from which position do I need to resume the coroutine? And it will actually jump to the position that you are resuming from. So the actual code inside the coroutine is in the resume stub. It's integrated there. And finally, you have the destroy stub, which is a call to free. So you're actually freeing the coroutine frame. I mentioned that there were multiple operators, but I didn't mention the last one, co-await. And this is where the fun really appears, because it's the most powerful one and the one you will most usually find in any program. It basically allows you to do all the fun stuff in coroutines, so you can do asynchronous jobs, you can do cooperative multitasking. There's so much stuff you can do. For instance, if you are talking about a waitable task, you can imagine this as, OK, I have a task which is very heavy at computational time, so I'm just going to put it here, I'll leave it executing, and I'll go execute something else. And once I am bored of waiting for it, I will go back and take the result and say, oh, OK, that's the result of my awaitable task. And to program this, it's actually boring. It kind of sucks. So you have to use callbacks, and it's really dirty. So programmers said, oh, let's use coroutines to have it nice and clean. And this actually really simplifies the things for every programmer out there. Now, to be very specific, what co-await does is to evaluate an awaitable object. And this awaitable object is nothing but a wrapper in which we will find an awaiter object. And this awaiter object is a real one, which is important, because we will have 3 functions that are executed one after the other. The most important one is await suspend. And in await suspend, we will have the actual things that happens once you are calling co-await. Here you have creating new threads. You might do things like resuming another coroutine. You can do whatever you want. Every program has different things here. And this is one of the functions that you should really look for when you're exploiting coroutines. Just to show you a very quick example, you are going to resume a coroutine, and this coroutine will co-await an awaiter. This co-awaiter will call the 3 functions in the order, so you'll have await ready, after all, await suspend. And in this case, we are going to execute some very expensive tasks, right? So I'm going to create some thread, leave it there. My other thread will go do something else. And this other task that is being executed eventually will finish, and then we'll resume the coroutine, meaning that you will be able to resume it wherever you left it. First, you call await resume, and afterwards, you go back to the coroutine. And later, if you want, you join both threads or whatever. This is a very simplistic scenario. Here's the fun part. coroutines, and specifically the task objects, is unawaitable. And this means that you can do things like awaiting coroutines from coroutines. And this is very common. So it allows you to do so much stuff, like you may have two coroutines that cooperate in some kind of task. You may have one coroutine that is in charge of maintaining a queue of other coroutines, and it is in charge of resuming them and destroying them. So there's so much stuff that is being used out there with coroutines. So let's look at what can we do with this. Our thread model is going to be very similar to what CFI assumes, which is, look, we are going to call some functions in our program, so obviously you need to know which is the address of them. So you need to have some ASLR bypass to know the address of these functions. And we'll have some kind of memory corruption, where there's going to be some vulnerability that allows us to overwrite some memory. I will go deeper into what exactly this looks like later. Also, you need some coroutine, of course. And you will need to have CFI in place in your program. Specifically, one of these 13 CFI schemes that we have analyzed, and we will go over them later. So the very basic observation that I'm sure all of you have done at this point is that the coroutine handle and the frames are in writable memory. And this is very bad, of course, because based on this, we devised two primitives that basically appear every time you want to do an exploitation with coroutines. The first one is frame manipulation, which consists of, oh, I found a coroutine frame here, so I'm going to overwrite it. And the second one is frame injection, meaning that you will inject new frames into the memory, either the stack or the heap or wherever, and you will link these frames, which are fake, but will now be used by the program like if they were real. So since we're dealing with CFI, there's a very easy way not to trigger it, which is let's not modify the pointer. So let's first look at what can we do without modifying the pointers. This is what we call as data-only attacks. And it looks like this. So you have a program, and we're going to have two co-await calls, so 3 suspension points, because the first suspension point is the very beginning. And maybe you will have a parameter. And this parameter, and this is something that happens in every coroutine, parameters are always copied to the coroutine frame at the moment you call the creation stuff. So you will always have them there from the very beginning, meaning that you can do something like this. You can have a coroutine frame overwritten, put a value that you want there, and actually put the coroutine index so that you go to the third suspension point and execute it with whatever data that you want. So it's like a very powerful way of doing database attacks. Variables are a little bit more tricky. So for instance, let's say you have this variable, and it's really only defined on the first suspension point and then used on the last one. It actually turns out that it's not, the compiler is smart enough to say, hey, this variable is not really used here, so I'm just going to initialize it in the last suspension point, meaning that even if you overwrite the coroutine frame with whichever value that you want, you will not be able to modify this value in a database attack. So these are kind of things that you need to take into account. For instance, if you have this other variable that is being used in some other suspension point, actually initialize, and then it's used in another suspension point, then this actually works because the value will be initialized in one of the suspension points, and you can modify this value for the next suspension point. There's actually more stuff than modifying data. So if you have some kind of heap allocated object, like a vector, this needs to be fed somewhere, right? You have to call free on this. And it's really always called at the very last suspension point. So you can do things like follows. Let's create a coroutine frame where I'm going to put a value, some pointer instead of this vector. And what I will have is an arbitrary call to free in my program. And this, as you can imagine, is a very useful primitive. And you can do cool stuff with it. Of course, you will have to have some metadata for the chunk and etc. But if you have ability to override the memory, these are things that can definitely be done. So really, how does this memory override look like? First, you can, of course, have an arbitrary memory write. This is the simplest scenario. But you can also have a stack-based overflow, which will override in the stack the coroutine handles that are used in the program. And this will allow you to say, OK, so I'm going to overwrite a handle. And now this handle, instead of pointing to the heap, maybe points to the stack again. And in this stack, I'm going to have an arbitrary coroutine frame there. You can also have a stack-based overflow, but inside the coroutine. And remember, every variable is a heap-based variable. So now you will have a heap-based overflow. And there is no stack canaries in the heap. The variable reordering that the compiler does is actually not really very well working with coroutines. So you can actually overwrite many variables. If you're in ptmalloc, like in Linux, you might also be able to overwrite some coroutine frames that are in higher memory addresses. So there's many, many things you can do. And at the very, very least, you will be able to overwrite the coroutine index with such an overflow. Of course, you can have a heap-based overflow, the classic one, where you just overwrite the heap, and you might be able to overwrite some frames. And it might be a combination of all of this. So you maybe are able to free a pointer, and this pointer actually allocates the next heap, the next coroutine on top of the other one. So there's lots of crazy ideas and things that you can do with this. But let's look at let's forget about data-oriented attacks, and let's look at what can we do with the pointers. Because as you can probably imagine, these resume and destroy pointers look very juicy for an attacker, and they really are. But we have to take into account that we're going to have CFI. So we are not going to be able to do things like return address hijacking, so no overwriting return addresses in the stack. Nothing weird like overwriting some virtual pointers. This is going to be accounted for by some of the other CFI schemes that we have. And also, the arbitrary code targets for indirect functions are going to be very limited because we have so many fine-grained CFI there. Or do we? Because it turns out that when we look at this, many of the CFI schemes do not account for coroutines, and they actually break when we compile them with coroutines. And most importantly, some of the CFI schemes that are out there and are fine-grained do compile the programs, and they do generate instrumentation for our coroutines. Sorry, they do generate the instrumentation for every function in the program, but not for coroutines. So the destroy and resume pointers are uninstrumented. And this really shows us that these CFI schemes need to be updated with how the programming paradigms evolve, because otherwise they will be left behind and they will not account for new things, like the coroutines. So in the end, we are left with two coarse-grained CFI schemes that are the most popular ones and are Intel CET and control flow guard, and will prevent us from calling functions from anywhere except the very beginning, which is still quite strict. But of course, yes, we can overwrite these resume and destroy pointers, but they're not really useful, right? Because we're going to call one function, maybe two, although I tell you that not every time you're going to leverage both the resume and destroy pointers, and they're going to have 0 arguments, which is kind of bad, because you want to call functions with arguments. So we devised a way of using coroutines to actually have infinitely arbitrary memory, arbitrary functions with arbitrary arguments. Specifically, we devised what we call a control frame pointer. And this is some pointer that might be the resume and destroy pointers, but also anything that indirectly points to these pointers. Let me show you how this looks like. So yes, this is a CFP, both the resume and destroy pointers, but also any handler that points to the coroutine frames can also be a point where you can override them that leads to control flow hijacking. You actually have lots of handles around. They are very popular whenever you have schedulers. And this is something that are very used in things like in browsers, in databases. I actually looked into some forums from Chromium, and they were thinking of implementing the events loop from some of the internal processes in Chrome with coroutines. So this is something that is really, really being used, even if this was only introduced in 2020 with C++20. And the third one is that you're going to have pointers that are internal to the coroutine frame and that I have not explained yet, but they are actually very interesting. So I explained to you what happens when you co-await a coroutine from another coroutine, but how did you come back? How does the other coroutine know where to go back after it's been executed? It's not like a function. You just not return. It actually uses continuation points, and you find this in every program that is using this kind of a scenario. So you will actually say from the first coroutine to the second one, OK, I'm going to set in your promise an object that is called the continuation, and that is a pointer to my handler, so that later, when you finish executing your program, your coroutine, you will call resume into this pointer so that you go back to the previous coroutine. And there's a second thing, which is, yes, we are co-awaiting coroutines, but are we going to have in a heap lots of different frames? Where are these destroyed? There must be somewhere where they are destroyed, right? And it actually, there is. So this is usually implemented as in the destroyer, meaning that once you go out of the scope of the co-await call, you will have an implicit call to destroy, meaning that you will have a destroy call to the coroutine frame that you just co-awaited. So every coroutine that you're going to be using has these two pointers, right? One that points to the next one, and that one points to the previous one. And based on this, based on all these CFFPs that we have identified, we devise infinite coroutine chaining, which is what we actually allows us to call infinitely many arbitrary functions. For this, you will have, when you're exploiting a program, you will have to find two CFPs, two of these pointers that I explained you before. And it looks like this. So the attack consists of injecting lots of coroutine frames in the memory, and these coroutine frames will do something fun, which is this. The first is that I am going to resume this malicious chain at the second suspension point, right after a co-await call, and right before a call to destroy. This will allow us to call destroy in an object that is in the coroutine frame, but which I arbitrarily control, meaning that I will destroy and the next element in the chain. But I don't want to destroy it. I want to resume it. So I will modify the next coroutine frame so that the destroy pointer is actually the resume pointer, meaning that when I call destroy, I will actually resume it. And this is how it goes. So I resume the next element in the chain, and the next element in the chain also has a hijacked continuation point. Sorry, not continuation point, but rather the coroutine object that I need to destroy. And this destroys the next element in the chain, and eventually you reach the last element. And in this last element is when you start making arbitrary calls. So you are going to destroy an object that you, again, control, and you are going to call destroy on an object that we call the trampoline frame, where I'm going to put the arbitrary call pointer that I want to actually execute. So you may call here system or whatever you want. After that, you return back, and you will continue the execution inside the coroutine until you reach the part where you're leveraging the second CFP, which was for us the continuation point. This continuation point is going to call resume on it, and we will actually go to a new trampoline frame where we will go and resume this pointer, which is, again, another arbitrary call. And this repeats. So we go, this moment we return back to the previous one, we go again to a continuation object, we resume it, execute another arbitrary call, and this continues for as many arbitrary calls as you want to make. So in this way, we have arbitrary calls, but we don't have arbitrary arguments. And for this, you have to know that every time you make a call with the resume and destroy pointers, the RDI register is actually fixed to the coroutine handler, meaning that you will be pointing to the coroutine frame itself. So when you call resume, it's not really very useful, because you're going to have this memory where you're going to have the resume pointer. It's not really a very useful argument to have. Destroy is a little bit more useful, so you're going to have some bytes that you're going to be able to leverage there, up to 8 bytes, but it's not really also not that useful in many cases. So based on this, we say, look, we control RDI, but not really what we point by RDI. But is there anywhere else where in a program made in C++ you use RDI? And actually there is. So every time you use some function that is a member function of a class in C++, these functions will actually use offsets from the this pointer, which is actually used as an offset from RDI. So every time you access a member variable in a class, you're actually using an offset from RDI. And based on this, we devise what we call a collision, where you're going to have your object, and it's going to load at a certain offset from RDI, but also we are going to have a coroutine frame where we're going to put at the exact same offset of RDI the values that we want to load, so that when you call this function, you actually load them in the registers that you want. This function, if you're very lucky, maybe that makes another indirect call. which in this case, you can set the registers and call the indirect function altogether, or maybe it just sets the registers, returns, and you leverage the next CFP for actually making the indirect call with all the registers already set. So I looked online and said, well, what is the programs out there using coroutines? And the most common one right now is the Windows terminal, but that wasn't very interesting. So I saw this other one, which is the Serenity OS operating system, which is an open source OS. And they actually use this thing. So they were playing around with coroutines for their browser. And I looked into this function, and I identified 2 CFPs. So I saw this destroy pointer, and I also noticed they are doing call await. So maybe I have a destroy call here. And they actually do. They're actually there, these CFPs. Unfortunately, they do have these codes, but they are not really using the coroutines yet. So they have the code, but they're not calling it. So just for this POC, what I'm going to do is I'm going to use a real CVE, which is from 2021, to overwrite an existing pointer in the program, which is an indirect call that you control with 0 arguments. And I'm going to use this to make 3 different indirect calls that have arbitrary arguments. So here in the right, you have the web content process of the browser. And this process is going to be running with Intel CET. So you can check this out under the proc file system. We'll see there that it has the shadow stack labels. And what I'm going to do is to, as I said, look where this pointer is. And this is an integer overflow that will lead to some memory override. And this memory override will be used to leak a pointer that I'm leaking there. So I'm going to use a malicious website that I prepared with the CVE, where I will actually override this pointer, and this pointer will jump to the functions that I just showed you with multiple CFPs. And as you see there, I have arbitrarily many calls. So I'm calling whoami multiple times, but also I'm doing something which requires more arguments. So as you can see, I'm really not limited to how RDI or any other register really look like. So these coroutines are available in every compiler out there. So they are in GCC, Clang, MSBC, and they all work the same. In Windows, actually, you might find some other complications and other things that you have to take into account where you're at the moment where you're trying to exploit these coroutines. So for instance, you will find that chunks are randomized. So maybe with a simple stack-based overflow that has turned into a heap-based overflow, you might not be able to overwrite coroutine frames that are in higher memory addresses. But you can also do DOAs and overwrite things inside the current coroutine frame, or overwrite the coroutine handle. So there's plenty of possibilities still. Bypassing CFG, as I said, is going to be very similar to bypassing IBT, because you will have just call the functions from the very beginning. And there's going to be other things like changes in the register convention, etc. But you can still do the same tricks that we did for having arbitrary arguments. So when we found this, we said, OK, I understand that you need to have these resume and destroy pointers in the coroutine frame, because the scenario you have with coroutines is that many times you're going to put them somewhere, and you're going to forget about them, and then you need to come back and see, oh, this is how I resume the coroutine. So there needs to be something in the coroutine frame to actually tell you how to resume and destroy it. But it's not very good to have the pointers there. So what we suggested was to say, OK, let's have an identifier, something that tells you where to look in some kind of table that is in read-only memory. And yes, you can modify this identifier, but this is not as powerful because you're not able to just call any arbitrary function with this. Finally, there's a final thing that by accident protects and allows you to have coroutines safely in a program. It's called heap allocation elision optimization. And this moves the coroutine frames from the heap to the stack. And as a byproduct, it actually stops using the resume and destroy pointers in the coroutine frame. It's actually not documented to do this, but we found it to be doing it. Now, in reality, it's extremely hard to get Halo. And if you have a very simple program, you will probably get it. But if you don't, and you don't program your program with coroutines with it, you will probably not get it. And basically, you need the compiler to say, OK, I need to inline these functions. You need everything in the same translation unit. You need to be able to have to know the whole scope of the coroutine. You need to know if it's resumed and destroyed in the same place. So there's really lots of assumptions you need, and unless you program your program with Halo in mind, you will not get it. And most of the programs I look at there, they are not getting it. And also, not every compiler supports it. So GCC does not support it. Clang does support it, but I actually found that it's broken for some reason. I think it's probably a bug in the latest versions of LLVM. And MSBC actually started using Halo after we reported this to Microsoft in version 17.13. But it's really not there, so it requires you not to compile with a flag that is actually by default in Visual Studio. But it's really getting improved. So also, I found before coming here that in the very, very latest version of MSBC, the developers are actually playing around with how the coroutine frame looks like. And they actually moved the promise to the very last position of the frame. And they are now allocating huge frames where it looks like you might not be able to leverage a heap overflow unless it's very big. So it looks like they're modifying the coroutine frames. It's not really perfect protection, but at least it's getting somewhere. So if you're interested in this project and you want to check out some exploits, some pokes that we discussed, if you want to learn more things about it, what I discussed today is just the basics of our research project. There's so much more things that we have documented about how coroutines work and how you can exploit them. So just go to this repository, and in here you will find all the information. Thank you very much.